Hey everyone, what's up? This is Steve here. Today let's go through another LeetCode problem 1268, search suggestions systems. I thought this is a very typical or classical problem that we encounter on a daily basis, that we can take a look at the simplified version of how it can be implemented. There are multiple ways you can complicate this problem in many different ways. For example, if you just type the weather, when you type THE space WEATHER, these two words into Google, you will see everything. You will see a lot of different words being auto-suggested. How that could be implemented. This is a very simplified version of that complex system. So let's take a look here. Given an array of strings, products, and a string search word, we want to design a system that suggests at most 3 product names from products after each character of search word is typed. So it's exactly like your search experience on Google. Suggested products should have common prefix with the search word. If there are more than 3 products with the common prefix, return the 3 lexicographically minimum products. So this is a gigantic simplified version of Google auto-suggestion, because Google takes a lot of factors into account before they auto-suggest you anything. But here, for simplicity, we're just going to return the 3 lexicographically minimum products. Now, it's asking us to return list of lists of the suggested products after each character of the search word is typed. Let's take a look at what that means. So given products, this is basically the index of Google's entire dictionary, entire index of to service customers search, right? So this index is a fixed index. This is another simplification, right? Mobile, mouse, money pot, monitor, mousepad. So there's a total of 5 words in the entire index of this search auto-suggestion. So the search word is mouse, and the output is 5 lists. Why 5? Because there's this search word, it has a total of 5 letters, right? So the first list responds to the first typed character, which is M. M, it has mobile, moneypot, and monitor. Why these 3? That is because these 3 are the lexicographically smallest 3. All right, and then the user types the second word, which is O. So now it has MO, these 2 letters. So it returns the same 3 lexicographically smallest words, which is mobile, moneypot, and monitor. And then continue on. The user types the third letter, which is U. So now the search term becomes MOU. Then the response to that MOU search term becomes mousepad. It's not mobile, moneypot, or monitor anymore. That is because the third letter showed up. It is U. None of these match to U. So any words that match U, the first 3 will going to be showed up. If there is no 3, we'll just show whatever that we have. In this case, it's 2. The list goes on when the user types S and E. So it shows up here. So this is how the system works. To me, the first idea that jumped into my head is to implement a trie. So that would be a most ideal solution in my head. But I also want to discuss, I saw a lot of people coming up with very creative solutions. Basically do a prefix. You sort the products and then you do a prefix binary search. That would help solve the problem as well. But I thought this is a very good opportunity to just practice implementing Trie, which is a very efficient data structure to help with such a use case. So that's what I'm going to implement in this video. So if you would like to learn that, feel free to tag along with me to let's revisit how a Trie could be implemented. Of course, you can optimize this in many other ways to optimize time complexity and space complexity, and to get rid of Trie completely, you can use sort the products and do binary search based on the prefix. You can do that as well. Just comment down below and feel free to let me know how you guys approach this problem. I would really appreciate that. So with that said, let's just solve this problem using Trie. So first we'll implement a Trie. So since this given products, it's fixed, it's not a stream of strings that keeps coming in that we need to update the entire Trie or the index. We don't need to do that. So we can just statically build this Trie, and then we'll just loop through every single substring from the beginning 1 to all the way to the last character of this search word, and then we can find all of the matched lexicographically smallest 3 words into the final result. This is the entire idea, but I think it would be cool to implement Trie, just to revisit the logic. It's very likely that you might get asked during a real interview that the interviewer wants you to implement Trie. So let's just practice this one more time. And also I'll put a link above here to point you guys to the video that I made a long time ago, how a Trie could be implemented. So feel free to check that one out as well. So now let's build it out. So first I'm going to implement a Trie node class. Oops, I think it's lowercase. Trie node. First is a character, and then second I'll have an array. I'll call it children. And then next, I'll have a boolean called isWord. Then I'll have a constructor for this class. I only need to take one, which is the C, which is the character. That's it. Now next, let me just build this Trie tree. Build Trie. What we need is this products. So now let me implement this Trie tree here. Build Trie node. No, not Trie node. It is this products. Let's implement this. And the return type is Trie node. Make it private. So first we'll have the common technique is that we'll implement an empty Trie node as the root node. So here we'll just have an empty character here. Now next, what we'll do is we'll go through the string list products. For each of the string is basically the product is a string. We'll just insert it into this product root, and then we can just return root. Okay, now let me implement this insert method. So root is Trie node. Trie node is the root. Product is a string. Private. This can be void. That is fine. So first we want to have this Trie node. I'll call it node root, and then we'll go through every single character of this product. Length here. Go through every single character of this product. We'll have a variable called C, just to call it product chart at, because we're going to refer to that many times down the road. If node children C minus A is null, then we're going to instantiate a new object, a new Trie node object, which is going to be Trie node C here. And then we'll move this node to its children to let it continue. Node becomes children C minus A. And in the end, after we iterate through this product, this string, what we want to do is we want to mark this one as a word, because all along the way, for example, if it's mobile, M is not a word, MO is not a word, MOB is not a word, etc. until it reaches MOBILE. At E, at the character E, we're going to mark this boolean isWord to be true, because we know we have a valid word instead of just a substring here. All right, so with these three functions, we have finished building the Trie tree. Now next, what we're going to do is that we're just going to go through every single substring of this search word and try to find all of the strings that do match, and we return the three smallest lexicographically words. Search word length I++. Okay, so first we'll have initialize a variable. I just call it result new array list result. Next, we'll just add things into this result. I'll just call it find top 3. All right, so what we'll have is search word substring 0 to I. This actually needs to be I smaller than or equal to search word because the ending index is exclusive. All right, and it needs to start from 1. That is because the first one is a valid character. We need to have a valid non-empty character. Find top 3, and then in the end we just return result. Now the problem is that we need to implement this. The type is going to be a list of strings. Find top 3. First one, we need to take in root as well. All right, so first one is root. Second one is just a search term. All right, this one can be private as well. Next, we'll just go through this trie node to find all of the search terms, or to find all of the strings that match this search term. So how we go about this is, so this is the beauty of trie tree. Everything is already sorted lexicographically already, the way that we are going to traverse this. So it's guaranteed that we are going to find the 3 smallest lexicographically words, right? So we'll always check if the result is greater than or equal to 3 already, then we can just simply break out and return. All right, first step, I'm going to have a result, initialize an array of list, and an array list of strings. Array list, return result. Next, we'll have a temp variable. I'll just call it node to hold the root because we are going to traverse down. We're going to use this variable node to traverse down this trie tree in all different possible directions. First, we want to find at the level where this search term ends, because if, say, the current search term is MO, we would like to go down to the level of O of the current trie tree, and then from the level of MO we continue to go down the trie tree. It could go any different directions, but we'll go through the alphabetically increasing order, lexicographically increasing order, which is guaranteed to give us the correct result, right? So we'll go through this char C search term to char array. So if node children C equals null, that means, for example, this trie node, it doesn't have even O at the second level. That means we can return nothing, right? MO, if you type MO, the trie tree node at the second level, it doesn't even have O as its child. We can just simply return nothing. There is no matching keyword if you type MO. In that case, we'll just return result, in which case right now it's an empty array, right? Otherwise, we'll just keep it, let it flow down to its children C minus A. Okay, so this for loop will help us to bring the node to the level where the current search term has ended. For example, if we typed MO at this current point, so this node is currently at O at this level. So next, we're going to find all of the possible full words within this trie tree under this O's level, right? All right, first we want to check if this one is a word already. If that is the case, we'll add this one, we'll add this one into the result first, because this is a valid result. For example, if there's a word called MO, it's just called MO in the trie tree, we'll add this one as well in the final result, right? And then at this point forward, what we want to do is that we want to do a DFS. We'll just continue to search for every level under O. We'll just go through all of those children, right? So for trie node child, this one, which is node children. First, we want to check child is not equal to null, because if it doesn't have anything, it's a null. We don't need to spend time over there. And then we can initialize I just call this result to go through. Here we'll have another function called DFS to basically do the depth first search. What do we need to take in? First is the point where we're traversing on of this trie tree, which is this child, and then we'll take search term, and then we'll take a new array list. So this is going to be the result. In just a second, we'll implement this DFS function, but let's have this full logic here. Result add all, this result in here. And as I said, we're always finding the lexicographically smallest words first. So in that case, if this one is greater than or equal to 3, then we can just return result already. Result, we can return result, and we need to return result only the first 3 items. That's all. That's good enough, right? All right, this is the full logic. Now let's quickly implement this DFS function. Private, it's going to be a list of string, DFS, try node, I just call it, we can call this root as well. I'll call it word. This one is result. All right, how do we do the DFS? So within this DFS, first we want to check if the current root node is a word, right? If it is a word already, we can just add this one into the result. Result add, we want to result add, which is this one, word, plus this root char, right? So this is the one that we need to append. So for example, it goes down to one more level. It finds B. B is actually, if it's possible, mob is a word in the trie tree. We'll just append B to the current search term, which is MO. So MOB is added. And also here, we want to check if result size is greater than or equal to 3, then we can just return result here as well, right? We don't need to go further down. And if it's not the case, we want to go through try node child root children. We want to continue to do this. So first, again, we check if child not equals to null. We'll just call this DFS function recursively. This one is child. And word here, we need to add one more, which is this char, and then result. In the end, we'll just return result. All right, that's it. It's a little bit lengthy. It's kind of long to implement such a solution for this problem, but I thought it's very good practice to implement trie tree. Now, let me hit run code to see if there's any compile errors. It does. Line 24. Oh, typo. It does happen, always, all the time. So first it needs to compile first. Line 55, null pointer exception. Children, null pointer exception. Huh. Oh, null pointer exception. That is because I never initialized this. All right, I need to initialize this to new try node. It only needs to be 26. That's good enough because we only have lower English letters, right? All capitals are lowercase English letters. That's correct. That should be good enough. Let me hit run code again. All right, accepted. Now let me hit submit to see if there's any errors. Run code. Oh, wow, accepted, but it's pretty bad. Faster than only 5%. Memory usage is only less than 8%. Yeah, as I said, there are multiple ways to optimize this. Let me just hit submit again. You should have enough submissions to, wow, it's nothing improved. Well, this is just one way to solve this. As I said, if you just hover over to discuss, there are multiple brilliant solutions other than using a trie tree to solve this problem. You can do a sort of the products and then do binary search on the prefix that could solve the problem. Probably time complexity would be much better and space as well. But I thought this is just a cool problem to help us revisit trie tree, how you can implement this. Hopefully this video does help people understand. If you want a more visualized version, I'll put a link above at this video, I have a more detailed video to describe how a trie tree could be implemented. Feel free to check that one out. If you think this video helps you understand the problem, please do me a favor and gently tap the like button. That's going to help a lot with the YouTube algorithm, and I really appreciate it. And don't forget to subscribe to my YouTube channel as well, as I have accumulated quite a lot of different LeetCode, data structure, algorithm, Amazon Web Services certification exam, how you can prepare and pass those exams, all of these different types of tech videos on my channel. Feel free to check them out. Hopefully I'll just see you guys in just a few short seconds in my other videos. Thank you very much for watching.